Hello everyone, so I'm back with a new video and in this tutorial we will be solving course schedule problem of LeetCode. Code. So let's see what the question says. So we are given a number of courses, num courses, okay, that's represented by num courses, and each of the course that you are given is numbered from 0 to num courses minus 1. Fine. So to solve any course, let's say I want to complete a course, for them I have some prerequisites. What does the prerequisites tell us? So let's say that a prerequisite of AB is there. What does it mean? It means that in order to complete course A, first I have to complete course B, right? B is a prerequisite of A. As given here, 0, 1, right? It means that 0 has a prerequisite of 1. In order to complete course 0, you have to first complete course 1. So what's the gist of the problem is, if you can finish all the courses or you can complete all the courses, you return true, else we return false. Fine. Let's find out how to solve this question. Okay, so let's take this example. So what does this say means that, let's say 0 has a dependency on 1 or a prerequisite of 1. 1 has a prerequisite of 2 and course 2 has a prerequisite of course 3. Fine. So how can we solve this? So we can simply say that I can start off from course 0 as it does not have any prerequisite. After completing this, the prerequisite condition of 2 will be over. So I can go and visit this, complete this course 2. After completing course 2, I will complete course 1. And after completing course 1, I will be completing course 0. Fine. So my flow of courses will be first 3, sorry, then 2, then 1, then 0. Right? This is how my flow of courses completion is going on. Right? Let's take some other example. So as per this example that I have taken, let's say 0 has a prerequisite of course 1, course 1 has a prerequisite of course 2. Now course 2 has again a prerequisite. What is that? Of course 0. Right? So what we say that 0, 1 and 2 are having a dependency cycle in between them. Fine. 0 has a dependency on 1, 1 has a dependency on 2, and similarly 2 has a dependency on 0. Right? That's how a cycle is getting formed. So let's see how to solve for such kind of examples. Okay. So if I say 2 will be my starting point, can I say that? No, right? Because it has a dependency on course 0. So if I say, can I start from course 1? Again, no. Why? Because for that we first need to complete course 2. Can I start from course 0? No, because for that I have to first complete course 1. So we see that since there is a dependency cycle, inside this particular cycle, we don't have any starting point. None of the courses firstly can be visited or completed. Right? If I try to visit any of these courses or complete any of the courses first, what's happening? We are seeing that it has a dependency, and that dependency again is depending on some other dependencies. So we cannot visit any of these courses, complete them. So all their dependencies are remaining as it is. So eventually none of the courses inside this particular cycle will be solved. So in such cases, we say the answer is false. Now let's say I have something like this. 0 is depending upon some course 1. Course 1 is depending upon course 2. Course 2 is depending upon course 3, let's say. We have a course 4 again, and we say that, and let's suppose course 3 again depends upon another course 5, right? We have such dependencies. So what we say, how to solve such kind of problems? We say that firstly we will be solving course 4 and 5 independently, right? In any order, okay? 4 and 5 in any order you can solve. First 5 then 4, or first 4 then 5. In any order you can do that. Once these two are solved, I can go and safely visit 3. I can say that, okay, then after this 4, 5, I will be completing this course 3. Once this 3 is over, I can visit 2. Then once this 2 is over, I will visit 1. And after this 1, I can visit 0. So in this order, I can complete all the courses, okay? Either 4, 5 or 5, 4. Okay, then after this I can go and visit 3. Then after completing 3, I can complete 2, then 1, then 0. This is how my course completion order will be looking like. Fine. Now let's take a case like this. So here what we can see is that only one node is there that doesn't have any dependency, that is this 2. I can first complete this and can remove this. Okay, remove the dependency on any other course that this 2 has, because it's already solved. So we see that once this 2 is solved or 2 is completed, 4 is getting reduced by one dependency. But this 1, 4 and 3, again we can see that this 1, 4 and 3, they are again falling inside a cycle, right? Earlier what we were doing, that in such kind of scenario, whatever we had, there were no cyclic formats, okay, inside the dependency, whatever we got. So now we have a dependency here. So again, firstly we can see 0 cannot be reached by, because for that 1 has to be solved. But can this 1, 4, 4 and 3, any of the courses that we have inside the cycle of 1, 4 and 3, can they be solved? No, because in order to solve this cycle, we should have a starting point that we cannot have, because we have a cyclic dependency here, right? So even if we try to start off from any of the nodes 3, 4 and 1, we cannot do that. Fine, because 1, 4 and 3 are dependent on one another to be solved, and that's not possible. So we can again observe that inside a dependency structure, that whatever we have made, if somehow a cycle is present, we cannot solve that, and the answer for such kind of cases will always be false. For these cases, the answer will be always be false. Just we need to figure out whether a cyclic dependency is there or not. So what you can observe from the structures we have made so far, this as well as the previous one. Okay, so we have two structures here. What you can observe, that each of the structure we have made represents a directed graph, right? A directed graph. And inside a directed graph, you need to judge whether a cycle is present or not. How can we do that? We can utilize topological sorting for them. Okay. So how topological sort can help us here? Okay, we'll first visit all those nodes or all those courses which don't have any prerequisite or in degree. If I say that 3 is a prerequisite of 4, that means 4 has an in degree from 3. Fine. That's how we will be representing a directed graph. Okay. So what we say, those courses or those nodes inside my graph that does not have any in degree, we'll first visit them. Fine. Visited 3 and 2. And once we visit them, we'll be removing all the edges, right? What we do inside topological sort, once we visit any node X, if it has any in degrees towards any other nodes, fine, or any edges, directed edges towards any other nodes A, B, C, we say that once this is visited, these edges will not be counted. So in degrees of A, B, and C will be reduced by 1. Fine. So effectively we remove the edges after visiting any nodes inside topological sorting. So 3 and 2 I visit, I am removing the edges that it has towards any other node. So 4 is the new node that I have that does not have any in degree. I will be visiting it. Okay. After visiting 4, I will be removing the edge it has towards any other node. So now 1 does not have any in degree. Fine. It has an in degree of 0. After visiting 1, similar goes to 0. That 0 does not have any in degree. So in the order that 3, 2 or 2, 3, then I go and visit 4, and then I go and visit 1, and then I go and visit 0. So what happens? Fine. We are able to solve in this order this particular example. But if suppose there is a cycle present, likewise we have seen here 1, 4 and 3 are falling inside a cycle. Okay. And let's say we have some other nodes as well, like this too. It does not have any in degree, right? So we can start off our topological sort from here. Once I visit this, I will remove the edges. But now once I encounter a cycle, okay, do we have any node here that does not have any in degree or whose in degree is 0? No, right? One of the in degrees of this 4 got reduced, but it still has an in degree, right? Or a inner edge from 3. So definitely its in degree will be 1 here. So inside a cycle, what we can observe is, for all the nodes, okay, for any of the nodes rather, the in degree will be at least 1, and none of the nodes will be having an in degree of 0. So effectively, any of the node using topological sort, we will be able to visit. Okay, that's not possible. So how to utilize topological sort here? Okay. So what we have observed that inside a cycle, utilizing topological sort inside a cycle like this. Just a minute. So our observation says utilizing topological sort, okay, inside a cycle, okay, we cannot visit any of the nodes because none of the nodes in degrees will ever go to 0. Fine. So if we apply topological sort over a directed graph, okay, so we say that all nodes can be visited if it does not have any cycle. All nodes can be visited in any order. Okay, we can form any of the orders utilizing topological sorting, and all the nodes can be visited if the particular graph that we are having does not have any cycle. Doesn't have any cycle. If it has, we cannot visit. If it has, we cannot visit all the nodes. The cyclic nodes or whatever nodes fall inside the cycle, those cannot be visited. So we say that okay, we can complete all the courses, we can finish all the courses if utilizing topological sort on our dependency directed graph, we can visit all the nodes. If suppose all the nodes can't be visited, we say that definitely there is a dependency cycle that's present. Fine. So that's how we'll be utilizing topological sort here. So let's go on to the coding part and let's see how to solve it. So let me first say that I have n number of nodes inside my dependency graph, that whatever I am able to or I am going to form. So I've stored it here. So yeah, since we are going to form a graph, I will be whatever prerequisite list is given to me, utilizing that I will be making a dependency or a adjacency list. Fine. So that will be vector of vectors that has slots for n nodes. Fine. Made that. Now what I'm gonna do, let us visit one by one all the prerequisites that we have, right? Now inside a particular prerequisite, inside the prerequisites list, okay, is also a list represented as A and B, and it says that okay, if you are to make a edge structure utilizing this, what is happening? B is having an edge towards A, right? Since A is having a prerequisite of B, that means that B is having an edge towards A. Fine. That's what is the analogy we will be having. So let's keep two things, right? Let's say that first node A will be storing whatever prerequisites of I has in its 0th index. Fine. Similarly, we say that prerequisites of I will be having whatever in its first index will be stored inside B. Fine. Now we need to push, we need to make an edge structure utilizing, or we need to form the adjacency list. So what I say, adjacency list of B, right? B is having an edge towards A. So let us push whatever inside the list of B, or we can say that this B is having edge towards what other nodes, let's say XYZ, those can be represented as a list. Fine. List of or adjacency list of B. For this B, we are making effectively a list of XYZ nodes. All those nodes that has prerequisite of B, or all those nodes that has an inner edge from B. Fine. So that's why inside adjacency list of B, I'm pushing back the node A. Fine. This part is done. Let me just wipe this out. What else have we missed here? Okay. To count for the in degree, right? Let us do that. So I will say I will be having a vector again, and that counts for the in degree of all nodes that we have. So we need to keep mark or a count for all n nodes. So let's initialize all of them with 0. I've done that. Now what I need to do is that since B is having an edge towards A has increased its in degree by 1. So I say in degree of A increased by 1. Fine. Okay. Now let's go ahead, or let us first keep a queue. Fine. This queue will be having the current number of nodes. Fine. All those that are having in degree 0. Fine. So at first, let me visit all the nodes inside the in degree counter. And inside this in degree counter, I will be checking if the ith node has an in degree of 0. So firstly, let's push them inside the queue to start off my topological sorting, right? Using these nodes, initially I will start off my topological sorting. Fine. I've initialized my queue. Now, till the time my queue is not empty, I will keep on searching for other nodes to be visited, right? So let's first keep a front, and that will be accessing the front node of my queue, and I can pop it out. Once I have stored it, I can pop it out. Fine. And yeah, let's move on. After popping out, let us, whatever front I have, let us try to visit whatever node inside the adjacency list of my current front I have. Okay. Since I am visiting this front F, all the dependencies of front F will be going over. Okay. What I mean to say is, let's visualize. Since I have a front F, okay, or a node F, it has edges towards XYZ. Okay, give me some time. So what I mean to say is that suppose I have a node F, and once I'm visiting this, one dependencies of X, Y, and Z should go over. Okay, effectively I'm removing these edges. So I say that once I'm visiting this, let's visit whatever is inside or whatever is kept inside the adjacency list of node F. Okay, for all of them, I will be reducing the in degree count by 1. Okay? I will be reducing the in degree count by 1. So let's do that. So let's initialize a loop for it, and so let me store the current adjacency list node of F inside node X. Let's say what I say, adjacency list of F of I. Okay, that's how I accessed it, and I will say in degree of X. Let's first bring it down by 1, and I will check one thing. If suppose in degree of X, if it is going to be 0, okay, it has what, it has marked that all its dependencies or whatever its prerequisites are, that are gone. Okay, that are completed. So I can push it to my current queue. I can say that okay, X can be a choice. Okay, I can visit at any particular order. Fine. Or X can be a choice. I can visit, X can be a course that I can visit after completing this course F. Fine. So I've done that. So I hope my topological sort is over. Okay, what we can say is that let's count, right? Let's have a count that what is the total number of cores we have at all completed. So we say that once we pop a course out of the queue, we have completed a course. So once we do that, we increase the number of count. Fine. So at end, after this topological sort is over, what we say, if suppose the count is going to be equal to the number of nodes that we have inside our graph, we return true, else we return false. Okay, let's try this. Let's try running this. Okay, so we made a mistake here. It won't be like this, but they will be first opening and closing brackets. So let me try running this. Yeah, so initial test cases are accepted. Let me try submitting this. So yeah, our solution is fully accepted. There is no problem in that. So yeah, our solution got accepted. So for topological sort, if we suppose we are having n nodes, okay, so in worst case we can have n square edges. So the time complexity that we require to solve for topological sort is big O of B plus C. So we can say in one of the most dense graph, or if we have a complete graph, right? So for them, if we apply topological sort at worst case, at any of the worst case that we have, our complexity may go to B plus B square, and that goes up to big O of n square, right? Effectively in complete graph, right? Effectively in a complete graph, you won't be able to visit any node. Any node we cannot be visited. Why? Because in a complete graph, if A is having an edge towards B, B will also be having an edge towards A. So we have a cycle. Okay. So we can do one thing. Since we are checking initially that which of the nodes are having to initialize our queue, right? Which of the nodes are having an integrity of 0, right? So for them, we say that for them, for checking them, we iterate from 0th node to the n minus 1th node. Let's say that. Let's see. So we apply an operation of big O of n. Okay. So in such scenarios, for a complete graph, we only do the visiting task to check for whether any node is having integrity of 0 or not. Okay. Effectively, there is no big O of n square operation in the worst case event. Fine. But let's say in any of the scenario that we may arise, we can have a big O of b square solution in one of the most complex graphs, let's say. Fine. And the queue that we are using right now, that queue we are using can hold a maximum of big O, sorry, a maximum of n nodes inside it, right? N nodes inside it, right? So at a time, queue cannot hold more than n nodes because there are not more than n nodes for our question. So at any time, we are having n nodes for both q as well as the in degree, as well as the in degree vector that we are keeping. Apart from this, we are holding edges, right? We are making an adjacency list of edges, and again that requires, if we have b square, this amount of edges, this requires b square extra spaces to be made, fine. So we say that we have big O of n plus n plus n square as our extra space because of the adjacency list we are making. So for our question, whatever solution we have solved, it requires big O of n square space complexity even. Fine. So that's how we have solved this question. I hope you liked the video. If you liked, please like, share, and subscribe. Thanks for your time.